everyone. Welcome to this session on modernizing your monolith using the Strangler Fig pattern. I just want to say that I really appreciate you being here to watch this session. My name is Anita Deenadayalan. I'm a developer specialist solutions architect here at AWS. I work for the DevAx team, developer acceleration team. In our team, we accelerate our customers to build secure, reliable, and scalable applications on AWS. You probably want to know what you can learn from the session today. I'll discuss the Strangler Fig pattern in the context of an e-commerce application, Storefront. Storefront application is already running on AWS. It's deployed on an EC2 instance with an Amazon RDS database. And an S3 bucket stores all the static assets like HTML, CSS, and JavaScript. So Storefront, they have a happy problem. The products sold by Storefront have become extremely popular in the recent days, and they have scaling issues. The application is struggling to take the load. Of course, they are trying to auto-scale their EC2 instances, but that's just not enough because certain functions need very high amount of scaling, but they are not able to scale up those instances entirely. So the user interface is hanging during the peak hours. The relational database can only handle so many transactions per second. So it causes a lot of database contention issues during the peak hours. So now these technical issues like the UX slowness and database contention, they're actually manifesting as real business problems. Because Storefront's IT team is spending most of their time, around 80% of their time on maintaining the applications and only 20% of the time on innovation. But that's not what they want to do. They want to be spending the 80-20 ratio should be reversed for them. They want to be spending 80% of the time on innovation and 20% of the time on operations. So the Storefront IT team, they are pretty cloud savvy. I do understand the benefits of modern architectures. They know that if they move into a microservices architecture, they are going to solve most of their problems. They can scale on demand. Their database contention issues can be resolved because from a one single monolithic database, they can actually move into multiple databases that can actually scale by themselves. Like the releases can be, like every microservice can be owned by individual teams and it can be released independently. So they will get a higher velocity of change and the blast radius for changes will be smaller because the functionality will be residing in microservices. But it's a business critical application. So they don't want to entirely bring down or cause any business disruption to their users. So they don't want to get their customers get affected during the migration. That's their key concern now. So they can do a few things, right? They can build a new system entirely and they can do a big bang migration. But the one thing that we can all be very, very sure of is if you do a big bang rewrite, it's one thing that you're guaranteed of is definitely big bang. Martin Fowler said that, and we all agree. So the solution here is to use the Strangler Fig pattern. So this pattern involves creating microservices around your monolith and gradually extracting out the features from the monolith and creating these microservices. And the application users will be immediately able to use these microservices and they will also be able to access the features on monolith. So the monolith will still remain the Strangler pattern, the Strangler Fig pattern. You will be creating the microservices from the functionality from the monolith and you'll be redirecting the calls in there. So, but before actually doing the actual migration, there are a few things that you have to think about. One primary problem that we always talk to our customers about, and we get questions a lot, is about how to identify the microservices. So when you are identifying the microservices, you have to think of a few important things. The primary thing is actually domain-driven design. You have to learn a little bit more about the domain-driven design and try to identify the business domain boundaries in order to identify the microservices. That's one way. There are so many other mental models you can think about it. So the other one is like you have to look at the natural divisions between the service classes. If you have a service class and it has a data access object associated with it and it writes to a particular database table, then that becomes one of those microservices. It can become a microservice. You should look at the release cadence. How often do you want to deploy the services itself. And we have many customers we go and talk to. When we advise them to split the services, I tell them, hey, look at it like from a point of where which service can go down along with this service. Do you think like, do you really want some of the critical functions to go down when you're making changes to some random settings? So that's something that you have to think of when you actually make a decision on how to split the microservice. And you can also think about the team location if you have a geographically split teams, because it's not a good decision to, like have a team working on a single microservice, but you have team in 2 different time zones. And then think about your performance and also think about your technology choices. For example, there are so many financial institutions for which use cases, like Python might be a better fit. And for certain use cases, you may want to use .NET or TypeScript. So that actually can make a decision point to split into microservices. And cognitive load is very important. So if there is a system or a microservice that is too big to reason with, then the service should be split. Software that is too big for our heads is actually working against the organizational agility. So now the application team, they have identified the features inside the microservice that needs to be split. And this is just a logical architecture here. So now a new feature request arrives. So the good decision here to make is don't put your new feature into your existing monolithic application. Create a new microservice for the new feature. And then, but at the same time, if you want to make changes to your monolith, if you want to make any bug fixes, they should be still allowed. But do not put any new functionality into your microservices when you're about to start on a Strangler Fig journey. So now we have 3 features here, inventory, order, and cart feature. So the inventory microservice has been migrated out now. So the order and the cart features, they're actually depending on the inventory feature. So one thing that I spoke about earlier is we want to minimize the business disruption. We want to make sure that the customers are not affected when we are trying to migrate out. So that means that I want to reduce the regression. So when I want to reduce the regression, I don't want to be touching the code of the order feature and cart feature at this point of time. I've migrated out my inventory feature, but I want to make the changes to the monolith minimal. So what I have to do is I have to introduce an anti-corruption layer. This is very important, okay? The anti-corruption layer is very important because it enables you to talk to your microservice without having to touch your existing features. The anti-corruption layer will act like a facade, or it will act like an adapter. Think of the Gang of 4 patterns, facade or an adaptive pattern. So it will help to convert the calls, like the order feature and cart feature will still be talking to the inventory feature, but internally the inventory, you will write a call to talk to the anti-corruption layer, which will convert the call and call the inventory microservice. And when you get a response back, it comes back into the order and the cart features. I know it's a little bit of a complex concept, but I don't have a lot of time right now. So if you have any questions on the anti-corruption layer, I'll be out there in the modernization booth after this session, and you can come and talk to me. Okay, and now the Strangler architecture will look something like this. We will still have the EC2 instance talking to the Amazon RDS database, and then we have the AWS Lambda and RDS that have been migrated out. So we have migrated out one feature. Now we have taken out the inventory microservice, but the common monolithic database, it actually remains. This means that we need to sync data between inventory and microservice because the monolith might have individual dependencies. It could have some downstream dependencies. So in that case, the solution is to sort of introduce a queue and a synchronizing agent. The queue and the synchronizing agent will sort of like whenever inventory microservice makes any changes to the database, it will be sent to the queue. Think of event-driven architectures here. The event will be sent to the queue, and the synchronizing agent will help to update the monolithic database with that data that has been updated. But one thing you have to watch out for is eventual consistency here. The data in the monolithic database will be eventually consistent. It will not be immediately available. There may be a 1-second delay by the time it gets to the monolithic database. And you need to set this expectation with your end users. So we are further strangling out. We have taken out the order service. Here the ACL, the anti-corruption layer will still remain. And finally, the architecture is going to look something like this. We have a cart still on the EC2, and we have the Lambda DynamoDB. And like the services have been migrated out. So finally, we are migrating out the cart microservice, and we just have a shell that is remaining there. And this particular shell can be decommissioned, and this will be the final strangle state. I'm sorry, I'm going a little bit fast here because the next thing I want to talk about is about the complexity of distributed architectures. So that's a little bit more important. So the strangled architecture will look something like this. If you see here, the Lambda function themselves, they are implemented in different technologies. And I'm using a different database for the different microservices. It's sort of intentional because I wanted to talk about polyglot persistence. Here we are using use case specific databases. We are talking about purpose-built databases here. So this particular microservice, it only uses a database that is fit for purpose. Similarly, if a microservice calls to use for Python, then you should just write it in Python and not get stuck to any normal, any particular language, I would say. So if you want to learn more about purpose-built databases, you have to attend the last session on this track, which is how to handle your data in modern microservices architectures by Kostuba and Joel. So the next thing I want to talk about is the distributed complexity, how the services can interact with one another. And now you see that the data has been distributed across different databases. I want to talk about how you can aggregate the data and how you can manage the distributed data themselves. So when two services communicate with each other, they can communicate either synchronously or asynchronously. This particular thing is very specific to synchronous communication. So what if the order service is calling the inventory service? And think of inventory service talking to a database, and this database is timing out. And from what I remember, like any database timeout, we could set it to 45 seconds. So you have like one call going in there, locking a connection for 45 seconds. And what if like hundreds of users are using this particular call? There is synchronous communication inside. So this means that the entire performance and like the system might go down due to performance issue because the connection pool is getting used up, the thread pool is getting used up. So it can actually lead to a lot of coupling, timeouts, cascading failures, coupling. So the solution here is to use a circuit breaker pattern. So the circuit breaker pattern is very similar to the electrical circuits at home. So it can prevent an application from repeatedly trying to execute a call. So for example, if you introduce a circuit breaker object in between the order and the inventory services, this means that the circuit breaker, if there is any abnormality, if inventory service is failing repeatedly, circuit breaker can actually trip the circuit and it will be able to return an immediate failure when this happens. And the circuit breaker can periodically check whether the inventory service is up and running or not. So if you want to learn in depth about the circuit breaker pattern, you can refer to my blog post on it, and I also have a link to my summit session talk, my last year summit session talk on the circuit breaker pattern. It's in the additional resources section later. You can just scan a QR code and get it. So if you are not using synchronous communication, you have to use event-driven architectures. Use a queue or a bus to post the events, and like the services will interact with each other using events. So it will be totally an event-driven system. So there will be frequently situations where you have to orchestrate workflows between your services. Maybe you may want to have parallel execution, or you may want to have some retry capabilities or repetitive execution. So in those cases, you have to use AWS Step Functions. So if you have, like for example here, order service, you are making an order. So you want to add to cart and lock an inventory. So this can be orchestrated using AWS Step Functions. And this is very much related to the Saga orchestration pattern itself. Saga pattern is for solving the distributed complexity issues. So what you do is you have to preserve the data integrity in distributed transactions across multiple services, then you use the Saga orchestration pattern. So if you want to learn more about Saga orchestration, again I have a link to my blog and my summit session link, and you can take a look at that. But for now, you remember that if you have to orchestrate anything between microservices, then think of AWS Step Functions. If orchestration, then Step Functions. So the next thing I want to talk about is the data ownership itself. The services, they own the data. So we don't want to have any regression cost due to the cross accessing of data. I don't want the order service to talk to the inventory database directly. I'm the inventory service. I want to own my inventory database. I don't want to have anybody else coming and talking to my database directly. Yeah, but from a humane terms, it's not right, but from a service terms, it's very important, because otherwise we are going to introduce a lot of regression issues in there. So the solution is actually to use the API calls. So when you use API interfaces, it is less likely for regression issues, because the APIs can be versioned. So you should never access a database directly. So okay, the next thing I want to talk about is data aggregation. So previously we had one single monolithic database, and you have a relational database with different tables, and you create like different types of joins. Inner joins, left outer join, right outer join, any kind of join that you want to get all the data. But we are going into microservices architectures. You don't have the privilege to do that, but the data is distributed across databases, and these databases, they can scale independently. At the same time, you want to make a single network call in order to aggregate the data. This is from a front-end perspective. If you want to do that, then you have to use AWS AppSync, which is our GraphQL service that helps you to combine data from one or more sources. The next thing I'll talk about is the data aggregation from backend. So like again I said, the services are owning the databases. I keep reiterating on that. I say the services are owning the databases because that is the primitive, okay? You just have to follow that. You can't have like multiple services having one database. Then you are sort of going against the microservices model itself. Now we have like these services owning the databases, but I want to aggregate the data. I have reporting needs. I have so many other needs. Maybe I have to project the data into a different database format. I want to probably like create a relational database format. I want to create a cache. I want to write it into a key key value database. So the solution for you is to use the event sourcing and CQRS patterns. So what we do is we collect all the events get written to an event store, which is called, here I'm using Amazon DynamoDB. An event store is very much similar to the transaction log for databases. If you go and look at how their relational databases operate and how they can do point-in-time recovery, it's because they are using transaction log, which is actually again an event log, something very similar to event log. So that's something that we create, the event store. So the event store, using the event store, so we can create relational database processes, or I can create a cache processor, or I can create a NoSQL database processor. So one single source of truth, I can actually project it into different formats. Okay, so if I want to create another data store, I can do that from here. And this is actually the command query responsibility segregation pattern. So the write side is called the command, the read side is called the query side. So today I actually spoke about the migration into microservices architectures and the Strangler F pattern itself, how it helps to bring down the transformation risk. Then I spoke to you about anti-corruption layer, which is very important. And I spoke about distributed complexity. Then I spoke about the circuit breaker, event sourcing, and CQRS patterns. So these are, like I have written some blogs, and I have had like few other summit talks where I talk about a number of patterns. So these are the QR codes for that. So to learn more about AWS services, you can visit skillbuilder.aws. So and with that, I would like to thank you again for taking the time to watch this session and being here. I really hope that my explanations have been helpful and will help you to apply the patterns in your distributed applications. I just have one final request for you. Please help to fill in the session survey. It will only take a minute of your time, but it will really help us to understand how we did today. And I hope you enjoy the rest of the AWS Summit. Thank you very much.